An organic molecule with the formula C8H8O2 gives the following infrared spectrum and proton NMR spectrum. Identify the molecule that best correlates with these spectra. So the first thing that I would look at for this is I would look to the infrared to get an idea of the functional groups that are present. And so I see this really broad peak here in the CH stretching region, really broad. It's overlapping those CH stretches. So this is all the bonds to hydrogen region, overlapping the CH stretches. This is really characteristic of the OH of a carboxylic acid. And so if we have a carboxylic acid, that's this general functional group, I would expect to also see an intense peak for that carbonyl, and here it is. So this is the double bond area. This is roundabout where we would see a carbonyl. We see that really intense peak for that polar carbonyl. So that's the carbonyl of the carboxylic acid. And then I might also notice that I've got this sharp peak fairly close to 1600, and that looks like a benzene ring. So now that we've got some good ideas about the functional group, we can take a look at the possible molecules. And so we can see that the first one is an aldehyde, and this is not an aldehyde IR. It is not what it looks like. We would not have that big OH stretch for an aldehyde. This B is a carboxylic acid, and it's an aromatic carboxylic acid, so that's a possibility. C is also an aromatic carboxylic acid, and then D is an aromatic ester, and so the ester again would not have that OH. So now we want to look to the proton NMR spectrum and see what we can identify here. So we could start with some very basic pieces of information, such as the number of signals. So if we were to look at this first carboxylic acid and predict how many signals we would expect to see, so we would have one for that carboxylic acid. You'd expect to see this CH2 as another signal. And then you've got a plane of symmetry in your benzene ring. So you would expect to see that the two hydrogens that are both next door to this substituent would be the same. These two hydrogens would be the same as each other. And then finally that end hydrogen. So for this molecule here, I would expect to see 1, 2, 3, 4, 5 signals in the proton NMR. And just at a really quick glance, we have 1, 2, 3, 4. So this is not matching. So let's take a look at C and see if this is more consistent. So we do have a methyl group there at the end, and we have a plane of symmetry again through the center of the molecule. So the two hydrogens that are adjacent to that carboxylic acid should be the same as each other. The two hydrogens that are both next to the methyl group should be the same. And then we'd have the hydrogens of the methyl group and the hydrogen of the carboxylic acid. So here I would expect to see 4 signals. And we do in fact see 4 signals. And so let's make sure that it does completely match. The carboxylic acid protons should be very distinct. They usually show up between 10 and 13 or so. And so here we see that. That's the carboxylic acid proton. And then we see in the aromatic region a total of 4 hydrogens, 2 hydrogens plus 2 hydrogens, and that's how many aromatic hydrogens we have. And 2 signals in this aromatic region, these ones and these ones. So we can label these signals. I would say this is signal A. So that would be that hydrogen. This is B. So the hydrogens that are closer to that electron withdrawing group would have a higher chemical shift. So we'll say this is C. Should be these 2. And then finally, that 3 hydrogen singlet is the methyl group. And so that is D. So this matches. So our molecule is C that matches both this infrared spectrum and the proton NMR.